he said, he told me kind of, okay, there's this kind of this day where you should give a talk about the influence function and stuff. I said, yeah, sure, without knowing kind of what the theme would be. So that's why it's about classical influence functionals, but there is still some connection to quantum information because it's kind of talking about open systems, which kind of it's a small jump towards thermodynamics and their information theory, and the techniques that we're going to use here are actually all kind of based on quantum mechanical ones. So yeah, and I noticed this is being filmed, so I shouldn't say anything treasonous. Yeah. So we're going to talk about the influence functional theory, and the way and this is something that gets used in kind of open systems. So there you go. There's an environment and there's your open system. Now there's actually a kind of long history of kind of using quantum mechanical techniques to solve problems classically. So there's the example of Prigogine, who kind of decided to kind of recast perturbation theory in terms of Feynman diagrams. So there's a lot of kind of results that can be used from this. So what we're going to try and do here is we're going to try and talk about a way of kind of deriving some really important behaviours that you would kind of associate with open systems or kind of thermodynamic behaviour, like irreversibility and dissipation and kind of stochastic behaviour, using this technique. So, first of all, let's talk about, I'm getting cut off here. I'm trying to just move this over, probably for the best, if it's possible. Oh.
Is it a PDF?
It's a PDF, yeah.
Do you have it on full screen though?
See, I think I did, but it seems that
They
it's
have not opened with Acrobat. That's the issue. Yeah, but for some reason, is it this discrete?
this one there. Yes.
Let's see what happens.
Yeah. So half of it is on one screen, and there's this on here.
Sorry about this. No, it's okay. I don't know why. We haven't had this problem before.
It seems to be a problem kind of actually moving it from one screen to the other.
Yeah, but it's a funny thing or something.
You can maybe zoom out a little bit.
Oh,
The
yes. Okay.
Yeah.
That'll do.
Yeah,
Oh.
maybe we'll just go with
Still
this.
like that, yeah.
Thank you. Okay, so the first part of this talk is kind of, I guess, motivating why you would want to kind of use this influence functional technique at all. So we know that kind of microscopic dynamics are supposed to be reversible. You know, Hamiltonian evolution. You kind of send t to minus t. Everything looks the same, and you will have this kind of conservation of quantities like energy. But you know, this isn't what we see in real life. We have dissipative behaviour, dissipation and fluctuation. And to kind of describe that, you often want to use kind of statistical or stochastic description with it. And you know, one of the earliest examples of this is the Langevin equation. And so you naturally have this question arise of how is it that kind of, if you're saying fundamentally you have these symmetries that everything evolves microscopically in a certain way, how do you end up with a kind of statistical description of something happening? And the way, so here's the Langevin equation in case you've never seen it, that will be worrying. And you have this kind of stochastic term that you have to kind of evaluate on average. So how is this kind of normally achieved? How do you go from a kind of microscopic model to one where you have this statistical nature? And the way you usually do this is you take a kind of particular kind of Hamiltonian called the Caldera-Leggett Hamiltonian. So you have a system, and you have a set of oscillators on top of it that are kind of interacting in a linear way. So it's kind of harmonic bath with a linear interaction with your open system. And if you kind of take the kind of n equations of motion you have for it, and you try and kind of express your equation of motion for your open system in terms of these oscillators, you find that you get lots of terms that involve the initial conditions of your bath of oscillators. And once you do that, you essentially kind of cheat a little bit. You say, okay, because I've got these huge terms and they're kind of big products, I'm going to assume that they're kind of statistically simple. I'm going to insert kind of by hand a statistical term into this because I don't know what the initial condition of my environment is. So it's kind of, you can do it kind of more or less, in more or less detail, but ultimately there's a kind of, there's a moment where you have to kind of insert stochasticity in a statistical description kind of almost by hand. But once you've got that, you know, you have the kind of, all of these ways of kind of transforming between Langevin equations and stochastic path integrals and Fokker-Planck equations and anything else you might like to describe dissipative systems. Okay, so that's how it's done normally. But it turns out that kind of if you take a kind of, if you look at the quantum mechanical regime, doing this kind of ad hoc introduction of stochasticity actually isn't necessary at all. That there's an entirely kind of rigorous way of introducing these elements to your equations. And it's due to this influence functional formalism, which was developed by Feynman using path integrals. And the idea is that you kind of have a composite system, and somehow, once you put it into the path integral formalism, there's a way of describing the effect of an environment on a system without reference to that environment. And it turns out that the effective equation of motion you get out of this fulfills all the properties you like. So essentially, all we're doing here is kind of trying to say, can we do this in the classical case as well, to kind of get things like irreversible behaviour, and even to derive Langevin equations from this. And you can, but there's a kind of a bit of a setup. So rather than kind of introducing stochasticity by hand, first of all, what you have to do is you have to kind of put classical mechanics on the same footing as in quantum mechanics, which means using an operational formalism. So this is kind of the next part, Koopman von Neumann dynamics. Right, so what is Koopman von Neumann dynamics? Well, it's by these two guys, John Newman, who everyone knows, his two kind of obsessions in the world of computers and nuclear weapons, and Bernard Koopman. I've really only got the picture here because I think he really looks like Leslie Nelson, so I could think that every time. So what is Koopman von Neumann mechanics? So it is Hilbert space formalism for classical mechanics. So everything you know about quantum mechanics, kind of keep the same picture of the kind of formalism, that you have a wave function or a state that's evolved somehow. You have a kind of propagator and there's a kind of generator of these kind of time translations, which is some self-adjoint operator A. The only place that kind of the difference comes in is defining a fundamental commutation relation. So in quantum mechanics, obviously, Q and P don't commute. If you want to describe classical mechanics, Q and P do commute. And it turns out that if you use this commutation relation together with the Ehrenfest theorems, you can kind of uniquely specify what this object A actually is. So in quantum mechanics, you find that it's the Hamiltonian. But in classical mechanics, you find it's this kind of odd object called the Koopman operator, which involves these two extra operators called Bop operators. And these are actually defined by their commutation relations. They're not observables, but it turns out if you want dynamics, your operators can't commute with everything, so you have to include new things if X and P commute. So here you see that kind of there's one non-commuting operator for position and there's one non-commuting operator for momentum, and everything else commutes. The final important point about this is that if you kind of take this option of describing classical mechanics and you have kind of classical wave functions which when you square give you probability distributions, it turns out that kind of in the QP, the phase space representation, the equation of motion for your classical wave functions is actually just the same as it is for probability distributions. That is, it's the Poisson bracket, which is very important because the idea now is, okay, we have a formalism for describing the evolution of classical systems. All of this is kind of entirely deterministic evolution, right? Just because I'm talking about classical wave functions doesn't mean that evolution isn't reversible or that there's any kind of dissipation involved. Once I have the idea of kind of classical universe, which is described with Hilbert space, I can try and create, if you like, a classical path integral. This is the kind of the necessary step. If the influence functional formalism in quantum mechanics is something where you have to do it in a path integral, then you need a classical path integral, unfortunately. And taking the kind of the classical propagator with this Koopman operator, you can do the same kind of slicing up into infinitesimal propagations as you do quantum mechanically, and you end up with this. So this is a kind of functional integral over your kind of phase space, plus these other two kind of non-physical operators that you have to put in there with this kind of e to the IR. So this kind of R is the kind of classical coordinate of your action. And if you actually look at it, kind of see, okay, it's this lambda and it's this theta, and it's really just a kind of delta functional. It's conditioning the paths to kind of obey the classical equations in motion. So if you kind of want a physical interpretation for what the lambda and theta operators are, their eigenvalues are actually Lagrange multipliers to enforce physics. And here we go. So if you were to take kind of a localized probability density, right, so just a point particle, you were to use this kind of classical path integral, plugging everything in, it turns out that, you know, all you're doing is a delta functional on f equals ma, which gives you, you know, that at some final time, the probability density is also localized on wherever the kind of classical equation of motion would have taken you. So it seems like kind of a formal hammer at the moment. You know, this is the most elaborate way you can imagine of saying, you know, force is equal to mass times acceleration. Why would you do this? Why are you doing this to me now? But there is a point to it, I promise. So, there we go. So far we've kind of covered KVM dynamics and we covered the kind of classical path integral. Now we get to kind of why this is interesting. So in order to kind of describe why this is interesting, we need to start to think about a kind of composite system. In the same way as at the start I mentioned this Caldera-Leggett model for how you kind of heuristically derive along with an equation. The same is true for kind of getting the classical influence functional. So you have to imagine you have your kind of system you're interested in, an environment, and an interaction between the system and the environment. And we have our system kind of described, the total system described by some initial probability density, which we're kind of partitioning out into something that we're going to call the kind of open system and the environment initial density. Now, notice that kind of our environment can kind of depend on the system coordinates and momentum as well. And this is quite important because, you know, not everything is separable. If you have an interacting system, it's actually sometimes quite hard to disentangle it in some sense. Yeah, is anyone following the news on this? My God. Oh, I was thinking about it earlier. It appears the UK Parliament is actually a group of practical intuitionist logicians because they don't want a deal and they don't want no deal, so clearly they don't believe in the law of the excluded middle. Yeah. So, we have our composite system. Let's say this is our kind of total system. You can imagine that it has this kind of unitary evolution, and this is another reason why it's important that the classical wave function evolves in the same way as the classical probability density, because it means they're propagated by the same object. So I can talk about the classical wave function or just the probability density, and they're evolved the same way. So if I have my initial probability density and it's propagated forward, I can then kind of take the trace over the environment, just kind of integrate that out, and I get kind of the reduced system. At the same time, I can think about kind of just my reduced system, how does that evolve? How is it that kind of, if I didn't know the environment existed, what kind of evolution would that look like? So, you know, if you imagine the kind of quantum context, this is your kind of completely positive trace preserving map, right? Here I'm just going to kind of call it an effective propagated Q and say, you know, somehow in some sense it's going to depend on my environment. So if we take our kind of classical path integral and we look at it, we kind of evolve the whole object here with this classical path integral. So the path integral variables over our open system, our environment, and the initial coordinates for both. And then we take the trace over that. That will give us the state of the reduced system at some time t. Now if we kind of take all of the terms in this expression and kind of pass them out into the ones that depend on the environment, we can define actually the influence function. And this is, you know, it looks pretty horrible, but it's okay. This is the object that kind of defines the entire influence of your environment on your open system and its evolution. So, to put it differently, that effective propagator that we have that only talks about the open system and doesn't talk about the environment is defined in terms of this classical influence function. So you can see here is the delta functional enforcing Newton's laws, and then there's this extra bit on top. And it's this extra bit actually that's kind of quite interesting, because it's clearly now you've made your effective evolution something that depends, okay, it only is expressed in terms of the open system coordinates, but it is still a functional of your initial state, which means that, you know, if you think about kind of forwards and backwards propagations, any forward propagation from, let's say, this initial state is going to depend on the environment at that time t0. So if you were to kind of evolve this forwards, the backwards propagation then would also require you to know what the environment is at this new time, t1, to go backwards. If instead, you know, you've kind of lost the information of what the environment is as soon as you kind of take the trace over it at the start, then kind of taking the time reversal of this, using this object, doesn't send you back to where you started, because, you know, your environment's not the same as it used to be. It'll actually send you back to kind of some new state. So actually there's a kind of animation that hopefully will work. Let's see. So you have to imagine this kind of evolving with the forward propagator, and then this is taking the time reversal of the forward propagator. As you come down, see, so, and this is kind of necessarily so just by, as soon as you start talking about these effective propagators in terms of influence functionals, you see explicitly where the environmental dependence is coming from. This actually also has interesting consequences for kind of fluctuation theorems. When you just start talking about fluctuation theorems and you see that these kind of forwards and backwards are different, it really relies on this idea of kind of there is actually some kind of super environment to kind of equilibrate the environment once you equilibrate at both steps. Otherwise, kind of you're not kind of using the same environment, if you like, at the beginning and the end. So you've got actually no difference between going forwards and backwards. So that is the kind of classical influence functional in abstract. But I say kind of where does the Langevin equation come from? And there's kind of one more step to this. That once you've got that reduced path integral, there's a formal transformation you can actually make to kind of deliver stochasticity, if you like. So, say you've kind of got an influence functional for a certain environment model, which is going to depend on the initial state of the environment and the dynamics. If it can be cast in a certain form, which is this kind of object, then this kind of functional chi of q and p actually will turn up in the effective equation of motion for your open system. But if you can put the influence functional in this form, this is the effective equation of motion for your system. Okay? So let's look at kind of an example where you can actually kind of solve what the influence functional is. This again is your kind of Caldera-Leggett Hamiltonian. We're going back to the way you would kind of start with the Langevin equation. And it's just a bath of harmonic oscillators with the kind of linear interaction again, and this is just for kind of, this counter term is actually just it's kind of renormalization. It's to enforce translational invariance. So for that model, you can evaluate what the influence functional is if you say initially the whole system is in a thermal state. So if you do that, you get this expression for the influence functional, where this kind of gamma, the I omega in here is just the continuum limit of all the coupling constants to the different oscillators. And one thing you can kind of see immediately, or maybe you can't, this term is phi, right? It's got the form that I was telling you about here, that it's a theta q, and then some functional of the actual kind of observable coordinates. But then there's this term here, which is not of that form. So how are you supposed to kind of make an equation of motion out of this? And the trick is to use this thing called the Hubbard-Stratonovich transformation. Now, unlike in the kind of heuristic method, this isn't kind of, oh, I'm just going to throw stochasticity in there. This is a purely formal transformation. And so what does it say? Let's say you have kind of some system where its position at different times is kind of interacting with itself So, you know, its position at this time has an influence on kind of what it's doing here. It's a kind of two-body interaction. What the Hilbert transformation does is quite precisely turn these kind of two-body interactions into kind of one-body stochastic ones. So it only matters kind of, the position now kind of won't have a direct impact on what's happening here, but there's always some kind of stochastic thing happening at every moment. And to kind of understand how this works, I'm going to try and show you it explicitly. So if you had took kind of just a Gaussian distribution and you Fourier transformed it, right, you'd have this object. But there's two ways of interpreting this. On the one hand, this is the expectation of that kind of Fourier component, this e to the ikx. If your x is your kind of random variable, your noise, then this is clearly the expectation of it. On the other hand, if I look at this, I can evaluate this explicitly. So on this, so kind of evaluating this like this k, this kind of complementary variable, is a deterministic object. It's kind of k squared, it's two-body. On the other hand, if I kind of express it in terms of an expectation over a distribution, well, k is here, it's only one body, but I've got this x now as well, which is my kind of stochastic element. So this is essentially what the Hilbert transformation is doing. When you apply it to the influence functional, it's a bit more complicated because they're processes and you've got to do some other stuff. But it means that if you kind of use the Hilbert transformation on this kind of troublesome term here, you can turn it into one which kind of has the right form for a effective equation of motion, but you have to include this kind of stochastic object, which means that essentially you've kind of introduced stochasticity purely as a formal transformation. So as a result, if you do this now, you take your kind of influence functional and you look at what the kind of effective propagator is as a path integral. It's a delta functional condition on this object, where you kind of your real probability density of the open system is taken by the average of this, which means that kind of if you were to just take one of these kind of trajectories, it would obey this equation of motion, which is a generalised Langevin equation. The whole thing is kind of taken from your kind of normal Hamiltonian view of evolution, but by kind of expressing it in this path integral way, you can rigorously move through the steps to kind of get this stochastic object, and you can then actually kind of talk about its statistical properties precisely in terms of the microscopic parameters in your system. And naturally enough, Bayesian fluctuation is a spatial relation. And kind of one last animation, just to kind of show you that what's happening here, that like you can imagine the individual trajectories, taking the average of those, essentially histogramming them will make your probability distribution in the end. So kind of the problem is kind of thinking in terms of a single trajectory to begin with. That when you do the Langevin equation normally, you have this heuristic derivation, you'll think about point particles to begin with. And so you kind of have to push stochasticity into it and then have an interpretation for it. Here you start statistically, deliberately from the beginning, and you can find that, okay, I can then describe the evolution of my probability distribution in terms of some of these stochastic trajectories. And yeah, I think, so just to kind of summarize, rather than kind of using ad hoc stochasticity, you can kind of build everything up from kind of operational formalism, where you kind of turn things into a classical path integral. It's allows you to define classical influence functionals. Then with that, you have a reduced path integral from which the Hilbert transformation can be used to bring you from microscopic models, which are reversible, to irreversible, stochastic, distributive systems. And I think, that's about it. So, cheers. Sorry about that.
Questions? I have one. So
Okay.
since stochastic, classical, in pretty much like the quantums, where does the quantum differ?
Where does quantum differ? Purely in the fundamental commutation relation. In fact, this is one of the really interesting things about Koopman-von Neumann dynamics. It really nails down what's really classical about the world and what's quantum about it. And essentially, unless it's directly to do with your fundamental commutation relation, it's not a quantum effect, it's a statistical effect. It's just kind of people don't kind of sometimes it's very easy for people to kind of say just because it's in a quantum formalism that it must be a quantum effect, whereas unless it relies on this commutation relation, there's really no difference. It will produce kind of a different rule for how things evolve, and that's the only kind of consequence.